our team decided to use a tank drive system because our drivers find this easiest to steer with. Tank mode means that we have two joysticks, each one controlling a wheel. When both joysticks are pushed up, the bot moves forward, and when both are pulled down, the bot will move backwards. When only the left joystick is pushed up, the bot will spin right, and when the right joystick is pushed up, the bot will spin left. We used both of our large motors and four-wheel drive because we like the speed and control that it brings. We used ports 2 and 9 on the Cortex for our drive system. This year, our team designed a double rack and pinion system to help us complete many different tasks on the game field. The vertical rack and pinion is controlled by 6 up and down on the controller, and the horizontal rack and pinion is controlled by 5 up and down. We have one of our small motors on each of the rack and pinions. To control the system, we have each of the 2 pairs of buttons send a value of 0 or 1. Buttons 5 and 6 up send values of 1 when pressed, and 5 and 6 down send values of -1 when pressed. Then the game blocks that we used multiply these values by 127, which is the full motor power in a direction, and the subsequent value is sent to the respective small motor, controlling one of the rack and pinion. We use Cortex ports 3 and 8 for our double rack and pinion system. Gripper claw that is controlled by the 7 down button on the controller. It uses a servo to open and close. Similarly to how the motors are controlled in our double rack and pinion system, when 7 down is pressed, it sends a value of 1 or 0, which is sent to a switch block that sends the servo a value of -127 or 127, depending on if it is receiving a signal of 0 or 1. This makes the servo move from the -60-degree value to the 60-degree value due to the servo gear ratio that is built into the servo code block. The single servo here uses Cortex port 5. We used 2 of our 3 remaining servos to grab and release our cardboard detachable part that is meant to hold and dispose of plaque. These are operated by the 8 down button, and the same code is used as with the claw servo, except that it is sent to a pair of servos rather than a single. This pair of servos has a different range of motion than the single servo does. In order to achieve our autonomous function, we took 3 IR transmitter-receiver pairs and utilized the autonomous line-following function from the example provided in the VEX companion app, modifying it to follow a white line instead of a black one. This required rethinking through and editing the provided logic matrix to better interpret the 3 inputs from the trio of sensors that we use. When the 8 up button is pressed, it will use a switch to either suppress the values sent by the joysticks to drive the robot manually, or suppress the IR sensor values and autonomous mode. We also slowed down the drive motors while in autonomous so that the sensors have time to make the robot react before getting too far off track. We used digital inputs 1, 2, and 3 on our VEX Cortex for the autonomous function.
Thank you, MathWorks!